Work done as energy transfer. We already know the basic formula for work, which is F into S into cos theta. We also know this formula is only applicable when all the parameters involved are constant. So force, displacement, and theta, everything should be constant. Now let us try to define the work done. Work done is the measure of how much energy is transferred when a force moves an object through a distance. Whenever any work is done, energy is transferred from one form to another. And this is the basic which you have to remember for every single question. Whenever a force does any sort of a work, it is energy transfer taking from one form to another. So, for example, kinetic energy can be converted to potential energy or vice versa. Or example, potential energy could be converted into thermal energy and vice versa. So, there are various forms of energy transfer that can take place. But do not forget the basics that whenever any work is done, energy is transferred from one form to another. So let's analyze this with a quick example. So here, look at this image. We have a bucket which is lifted vertically with a force of 100 Newton for a height of 5 meters. So the bucket is being lifted up by 5 meters. So we have to figure out the work done. Work done on the bucket, we are going to use the formula Fs cos theta. So the applied force is upwards, displacement is also upward, so theta will be 0 degrees. So we'll write 100 multiplied by 5 into cos 0. That is equal to 500 joules. So 500 joules of work is done on the bucket. And according to this concept of work done as energy transfer, we can say work done by the woman transforms into the gravitational potential energy of the bucket. So the woman is doing a total work of 500 joules that converts into the potential energy of the object. In this case, the bucket is lifted up by a height of 5 meters. And that is why we discussed earlier that whenever any sort of work is done, it's an energy transfer taking place from one form to another. Let's try to solve another question based on this logic. So here we have a box of mass m. It is being pulled across a surface with a force F. The coefficient of dynamic friction is given, which means the surface on which the block is moving is rough. So we have friction. And the question is, what is the energy transferred to thermal energy while a box is moved by a distance d? So first of all, I will tell you the most common approach with a lot of students use to solve this question. We have to figure out the energy transfer. We have just learned that the energy transfer is nothing but the work done. So how do we find the work done in this case? So we can see applied force F is acting on the right hand side, and there will be a frictional force acting towards the left hand side. So a lot of students, what they do first, let's try to figure out the net force. So we will write capital F minus friction. Since the applied force and friction are always opposite, that's why we subtract them. And then the students apply the basic formula for work done, which is Fs cos theta. So in this case, we will write work done will be equal to the net force is F minus small f multiplied by the distance traveled in this case is d as it is given in the question. So we will write d, and friction is nothing but mu times the normal reaction, and normal reaction in this case will be equal to the weight of the object. So n and mg are equal. Hence, we can write down the final formula for work done as capital F minus mu mg multiplied by d. And based on this, students pick option B as the answer. But there is a flaw in this approach, although the steps are correct. So this approach is wrong only because of a keyword in the question, and the keyword is here. They have said, what is the energy transferred but to thermal energy? Just try to use common sense. If a box is sliding on a surface, of course, the surface will become hot. Thermal energy will be generated. So, only friction can do work which can be converted into thermal energy. So, the applied force, although it is going to do work, but that cannot be converted into thermal energy. So, let me write the work done by only friction that will be equal to the thermal energy which we have to figure out in this question. So let me repeat, since the block is moving on a rough surface, that is why the surface will become hot. Thermal energy will be released. So friction is responsible to produce the thermal energy. Hence we say work done by only friction is the thermal energy. And we will use the basic formula for work, which is Fs cos theta. So work done by friction will be friction F multiplied by distance d multiplied by cos 180 Now, why 180? Because the displacement of the object is rightwards, but the friction is acting leftwards. So the angle is 180 degrees. This will be equal to Q, where Q is the thermal energy. And now let's simplify the expression. So the value of friction is mu times the normal reaction, and normal reaction is mg, like we saw earlier. So friction is mu mg multiplied by the distance d. Cos 180 is -1. This will be equal to the thermal energy. Hence, we can write down the thermal energy which is produced will be negative of mu mgd. And if we look at the options, it is only in option C where we get the answer. Now, do not get confused by the negative sign. Negative sign is only to show that the energy is being released. But the question only wants us to find the magnitude of the work done or the energy, which will be option C in this case. Work energy principle. It states that the total work done is equal to the change in kinetic energy, which is final kinetic energy, minus the initial kinetic energy. So, according to the work energy principle, the amount of work done on an object is equal to the change in its kinetic energy. But there is a catch. This work done, this is the net work done, first of all. So, it is the net work done by all the forces acting on the object. So, we have to incorporate every single force which is acting on the object. So, that work done. Delta K is the change in kinetic energy of the object. So that is final minus initial kinetic energy. Let's try to solve a question based on this formula. So here we have been given the speed of a 20-kilogram box changes from 3.2 to 1.2 meters per second. Calculate the total work done on the box. Now, in the exam situation, if you get this question, students have this habit of going to the basic formula for work, which is Fs cos theta. But the problem is, force is not given here, displacement is also not given here. So the formula will not be useful to get the answer. This is where we use the second formula for work done, which is total work done is equal to the change in kinetic energy. So in this case, the final kinetic energy is half mv square, mass is 20, but the speed is 1.2 finally. Initially, the speed was 3.2. So if you analyze, the speed is decreasing, which means the object is decelerating. And then if you simplify, we will get negative 88. And we can say that the total work done on the box is negative 88 joules. Now, why is it negative? Because the force is decelerating. So even though, let's say the object is moving to the right hand side, it is continuously decelerating, which means the force is being applied in the opposite direction. And since the directions are opposite, theta will be 180, cos 180 was negative 1, and that is why this work done is negative 88 joules. And now let us summarize all the formulas which we have learned in this chapter so far. First is, let's start with the work done. Work done, basic formula is Fs cos theta, but remember this formula is only applicable when all the parameters involved are constants. Otherwise, we use the area under the graph. So that's the first approach. The second approach is to use the work energy principle, which we just discussed. Total work done is equal to the change in kinetic energy. Kinetic energy is half mv square. Gravitational potential energy is mgh. But do remember the concept of reference line. So any point above the reference line will have positive potential energy. Any point below the reference line will have a negative potential energy. For elastic potential energy, which is in springs, so the formula is half kx square. A lot of questions are asked on these two principles, work done by the spring and work done on the spring. So please remember the formulas. Work done by the spring will be negative of the change in elastic potential energy. So we will do initial minus final. In case of work done on the spring, that is positive change in elastic potential energy. So that will be final minus initial. So if we summarize, we can deduce that the work done on the spring is equal to negative of work done by the spring. So the magnitudes are the same, but the direction is opposite. And this is the list of all the formula which we will use to solve questions for this chapter. Here we have an object of mass 2 kilogram, which is having initial kinetic energy of 10 joules. It is coming to rest, which means this is decelerating. As it travels a distance of 3 meters along a flat, rough surface, we have to figure out the coefficient of dynamic friction. Now, there are various ways to solve this question. Either we can use the work energy principle, or we can use the CUAT equation or the Newton's laws of motion. So let's solve this question using both methods. So let me write method 1 using the work energy principle, which states that the total work done will be equal to the change in kinetic energy, which is final kinetic energy minus initial kinetic energy. Final kinetic energy is 0 since the object is coming to rest. Initially, they have given is 10. So delta K will come out as negative 10. This will be the total work done. Now, to figure out the total work done, we have to first figure out what is the net force which is acting on this object. So how do we do that? Let's draw the free body diagram. So the first force will be the weight of the object which is acting downwards, which will be balanced by the normal reaction provided by the surface going in the upward direction. Also, there is a frictional force which is trying to oppose the motion of the object acting in the leftward direction. Now, normal reaction and 2g, the weight, will cancel each other out. So the net force acting on the object is only friction. So the work done, let's write down the basic formula Fs cos theta. F is friction, displacement is 3 meters, and the angle between the frictional force and the distance is 180 degrees. So cos 180 will come out as negative 10. So the value of friction according to the formula is mu times the normal reaction, and normal reaction is m into g. So let's write down multiplied by 3. Cos 180 is negative 1. So negative sign will get cancelled out from both sides. Continuing ahead, mu times the normal reaction mg multiplied by 3, minus sign gets cancelled out. So we get a 10. Now, since we have to find the coefficient of dynamic friction, let us make mu as the subject. We will get 10 upon 3 mg, and mass of the object is given as 2 kilograms. So let's write down 10 upon 3 into 2, and the value of g we can take as 10. So 10 and 10 gets cancelled out. Hence, we get the value of mu as 1 upon 6. Hence, option A is the right answer for this question. We could have also solved this question using the Stewart equations, which are also called the Newton's equations of motion. And how do we do that? Let me write down the third equation, which states that v square is equal to u square plus 2as. Final speed is 0. Initial speed we don't know, but we can find it out. So the initial kinetic energy is 10 joules. So let's write down half m u square is equal to 10. Mass of the object is 2. So half into 2 into u square will come out as 10. So u square will be equal to 10. So directly we can put this value of u square in this equation. So we write 0 is equal to 10 plus 2 times acceleration, and the distance traveled is given in the question as 3. So if we make A as the subject, we will get acceleration as negative 10 upon 6. Now, what do we do after this? So we have to find the same acceleration but using another formula. So let's use the Newton's second law. F net is equal to ma. So acceleration will be net force divided by m. And we already discussed the net force acting on the object is only friction. Now, since the weight and the normal reaction are cancelling each other out, friction is the only resultant force. So the net force is friction. We have to divide that by mass. So the value of acceleration will be friction is mu times the normal reaction divided by m. In this case, normal reaction is equal to m into g. So m gets cancelled out. So we get acceleration as mu into g. Now all we need to do is equate this value of acceleration to the acceleration which we got earlier. So we will write mu into g. We can ignore the negative sign. So we will write 10 upon 6. G is 10. So G will get cancelled out. Eventually, we get the value of mu as 1 upon 6, which means A is the right answer. Now, bear in mind why we have ignored the negative sign, because in this formula, we have used the magnitude of friction. So the net force is equal to mu times n, which is the magnitude. And over here, 10 by 6 is the magnitude. That is why we ignored the minus sign. So A is the right answer to this question. A box of mass 2 kilograms is pushed and released with an initial speed of 10 meters per second. So let's draw that. It is moving on a rough horizontal floor. A uniform frictional force of 10 newtons acts on the box. So let's draw. Friction will oppose the motion. So in this case, we can draw the direction of friction to be left. The question is, what is the distance traveled by the box at the instant when the kinetic energy of the box is halved? So let's use the work energy principle to solve this question. We can also use the Stewart equation to solve this. So the change in kinetic energy will be final kinetic energy minus the initial kinetic energy. Initial kinetic energy is half m into v square. Now, mass of the object is given as 2 and the speed, initial speed is 10. So, eventually we can write initial kinetic energy is 100 joules. So, in the expression, we will write kinetic energy initial as 100. Now, the final kinetic energy is half of the initial. So, half of 100 is 50. So, final kinetic energy will be 50. 50 minus 100 comes out as negative 50. Hence, the total work done by forces acting on this object is negative 50 joules. Now, to find the work done, we already know the formula Fs cos theta. So, Fs cos theta. So, what is the net force acting on this object? So, the weight of the object will be balanced by the normal reaction. So, let me write 2g, which is the weight, will be balanced by the normal reaction. And that is why friction will be the only resultant force acting on this object. So, instead of force, net force, we will write friction. Displacement is what we need to find. Angle is 180 degrees. And why it is 180? Because friction is leftwards and the object is going towards the right. So angle is 180. This will be equal to negative 50. The value of friction is given as 10. So let us write 10 multiplied by d multiplied by minus 1 is equal to negative 50. Cos 180 is minus 1. Minus minus signs will get cancelled out. Eventually, we will get d as 5 meters. And that is why option B will be the correct approach. And that is why option B is the right answer for this question. Now, we could have also solved this question using the second method, which is the Stewart equation or the Newton's equations of motion. So let's write down. Let's call it as method number 2. So let's write down the equation v square is equal to u square plus 2as. Initial speed is given as 10. So we will write 100 in place of u square plus 2 times the acceleration multiplied by d. And d is the distance which we want to find. So initial kinetic energy was 100 joules. So final would be half of that 50 joules. So we can write down, since final kinetic energy is 50, let's write down half into mv square will be equal to 50. And mass of the box is 2 kilograms. So if we simplify this expression, we will get v square as 50, which we can use in this particular expression. So v square can be written as 50 equals to 100 plus 2 into acceleration multiplied by distance. Let's simplify this expression. So we can write 2ad equals to negative 50. Hence, a into d will be equal to negative 25. And since we have to find the d distance, let's make d as the subject. We will get negative 25 divided by acceleration. And how do we find this value of acceleration? We are going to use the Newton's second law, which is F is equal to ma. So acceleration will be the net force divided by m. Net force acting on this object is only friction, which is 10 newtons in magnitude. So the net force is 10, mass is given as 2, which means acceleration comes out as 5 meter per second square. So we can use this value of a in this expression. So let us write down d will be equal to 25 divided by a. We can ignore the negative sign. So 25 divided by 5 will come out as 5. Hence, the value of d is 5 meters, which was option B. So here we have a box of mass 2 kilograms starts to move on a level surface under the effect of a varying force F. The variation, so the graph is given. X-axis is displacement, y-axis is 4. So we need to figure out the speed of the box at a particular value of s, which is 5 meters. So let us try to solve this question using the work energy principle, which states that the total work done is equal to the change in the kinetic energy, which is equal to the final kinetic energy minus the initial kinetic energy. Now, initial kinetic energy of the object is 0 since it is mentioned that the box starts to move. So, initial speed is 0. So, initial kinetic energy we can write as 0 and final kinetic energy is half m into v square, where mass is given as 2 kilogram. So how do we figure out the total work done? Now we cannot apply the formula for work, the basic formula Fs cos theta. That formula is not applicable because the magnitude of force is not a constant. It is constantly changing. So that formula goes out of the window. So what do we do in such cases? We have to figure out the area under the graph. Step 1, let us draw a dotted line from the end of the graph on the displacement axis. So in this case, it is the x-axis. And then let us shade the entire region. This entire region's area we need to figure out because that is equal to the work done. So how do we figure out this area? Let us divide this entire region into two separate parts. One will be a triangle and then we have a rectangle. So over here you can see a rectangle where the length is 5 meters and the base height is 2. So the area of the rectangle will be 5 multiplied by 2, which is equal to 10. So we can write 10 over here. Now considering this triangle, the base of the triangle is 5, but the height will be 8. So over here this is 8. Just for clarity, let me show the dotted line. So this is point 0.8 and point 0.2. So the height of the triangle will be 8 minus 2, which is 6. Hence, we can say the area of the triangle will be half base into height. Base is 5 and height is 6. So we write this as 15. Area of the triangle will become 15. Hence, the total area of the entire region will be 15 plus 10, which is 25. Hence, work done we can write as 25, which is equal to half into m into v square. Mass is 2 multiplied by v square. If we simplify this, we'll get v square as 25 and the value of v comes out as 5 meters per second. Going back to the options, the right answer is in option A, 5 meters per second. A block of mass 16 kilograms is pushed and released along a rough surface at an initial speed of 2 meters per second. The block travels a distance of 16 meters and is brought to rest. We have to figure out the frictional force that brings the block to rest. So let's solve this question using both methods. Method number 1 is the work energy principle, and then we will use the Newton's equations of motion, which are also called the CUAT equation. So method 1, work energy principle states that the total work done is equal to the change in kinetic energy, which we can write as final minus initial. Now, initial speed is given as 2 meters per second. So, initial kinetic energy, let's write that half mv square, mass is 16 and the speed is 2 square. So, the initial kinetic energy will come out as 32 joules. But the final kinetic energy, we can write it is 0 because it is mentioned that the block comes to rest. So final kinetic energy comes out as 0. So the change in kinetic energy will be 0 minus 32. Hence, we can write down the total work done will be equal to negative 32 joules. Now, to figure out the work done, we have to figure out what is the net force acting on this object. For that, let us draw the free body diagram of the object. So the weight of the object 16g will act downwards, which will be balanced by the normal reaction. And then we have a frictional force acting towards the left. Now, since n and the weight are cancelling out, so the net force acting on this object is only friction. So let's write down the basic formula for work, Fs cos theta. F here will be friction. Now, the distance traveled is given in the question as 16 meters and the angle will be 180. Why 180? Because the friction is left and the box is traveling towards the right. So displacement is right, and that is why the angle between displacement and force is 180. So this will be equal to negative 32. So let's simplify. F into 16 into cos 180 is negative 1. And if we simplify this expression, we will get the value of friction as 2 newtons, which means A is the right answer. All right, let's solve this question using the CUAT equation, method number 2. So the equation is v square is equal to u square plus 2as. Final speed is 0 because the object is at rest, comes to rest. Initial speed is given to us as 2 meters per second. So we will write 2 square plus 2 times the acceleration multiplied by distance is 16. Now, if we simplify this expression, we will get the acceleration as negative 1 upon 8 meter per second square. So this is the value of acceleration. What do we do after this? We have to figure out the acceleration using the Newton's second law, which states that acceleration will be net force divided by the mass. Net force is only friction acting on this object. So friction divided by m. And mass is 16. So the value of acceleration is F upon 16. Rather, F upon 16 is the magnitude of acceleration. Hence, we can equate both the magnitudes. So F upon 16 will be equal to 1 upon 8. And if we cross multiply and try to figure out the value of friction, that will come out as 16 upon 8, which is 2 newtons. Hence, option A is the right answer to this question.